projectiles and horizontal projection. So we're going to start off by thinking about what a projectile actually is. And a very simple example of a projectile can be created if you simply take a tennis ball or some other kind of ball and throw it in the air, so it follows this parabolic arc. As you throw the ball in the air, you will give it some kind of initial velocity. It will decelerate because gravity is working against it, trying to pull it back down to the ground, until it reaches zero velocity at the top of its motion, here. Once it's reached its maximum height above the ground, it will then start to travel towards the ground, accelerating as it does so, because of course gravity is now working with the tennis ball, moving it down towards the ground. And this path is called a trajectory. Once the ball is released, it's not powered by anything. It has what we call momentum because it was given an initial velocity which allows it to carry on moving, but there are no other external forces acting. The only force acting is the weight of the object, i.e. the force of gravity acting on the object's mass. So let's think about the modelling assumptions that we make when we're investigating projectiles. Firstly, the projectile is modelled as a particle. It is not powered. It is given an initial velocity, but afterwards it moves freely under gravity. We assume that the effect of air resistance or drag is negligible, so the only force acting is the weight of the object. The projectile does not spin as it moves, and all motion occurs in one plane. If you think of a plane as a piece of paper, then this motion in the diagram below is all occurring in one plane. If the motion came off the paper, so out up into the air for instance, off the paper, then that would be motion occurring in more than one plane. So imagine in all of the examples that you do, because the particle isn't spinning or moving from side to side, it's just moving forwards and then down again, all the motion is occurring in one plane. It's important that you memorise this list of modelling assumptions. So we're going to start off our investigation into projectiles by looking at a simplified case scenario of horizontal projection. So let's imagine we start off at a height above ground, so at this position here, and we throw or project or launch an object horizontally like this. So it's given an initial speed of projection. Now, because we've thrown the object horizontally rather than at an angle up into the air, we don't see the full parabolic path. We only have part of the parabolic path. The particle will travel down towards the ground, like that, and it will have a velocity. So the velocity will look like that. Now, the velocity will be composed of two components, a vertical component downwards like this, and a horizontal component like that. So let's just label this. So that's the velocity, which is at a tangent to the curve. Let's think about the forces acting. What we're going to do is we're going to split the motion into two parts. Or two directions. And we're going to focus on each direction separately. I'm going to start off by focusing on the horizontal direction of motion. And let's think about what forces are acting. So the object is launched horizontally, But then after that, there are no horizontal forces acting over the course of the projectile motion. Remember, we said that air resistance and drag could be thought of as negligible, so we could exclude those from any calculations. So horizontally, that means there are no forces acting at all. So this means that horizontally, the resultant force, which I will call sigma F, to indicate the sum of the forces, is equal to 0. Now, if the resultant force is equal to 0, that means acceleration is equal to 0. Because, of course, we have Newton's second law of motion here at work. F equals ma, resultant force equals mass multiplied by acceleration. Now, if the resultant force is equal to 0, that means the particle, or the projectile, travels at a constant speed, horizontally. Just horizontally. And this constant speed is equal to the initial speed of projection, the initial horizontal speed of projection. So if we call this initial speed of projection u, let's pick this moment in time here, and the horizontal component of the velocity will be u. And we can pick any point on the particle's journey. Let's draw in the velocity vector. It's got a vertical component and it's got a horizontal component, and the horizontal component will always be equal to the initial horizontal speed of projection. But what happens when we analyse the motion in the vertical direction? Because this is slightly different. So vertically, there is a force acting, and the only force acting is weight. i.e. the effect of gravity on the particle's mass. Now, this means that the acceleration, which is caused by this resultant force of just the weight, is the acceleration due to gravity. So the acceleration is equal to g, or 9.8 meters per second squared. And what's very relevant is that this acceleration is constant. The weight is constant throughout the journey of the particle's motion. So that means the resultant force is constant, which means the acceleration is constant and is equal to 9.8 meters per second squared. Now, if we have constant acceleration, and actually we have constant acceleration both horizontally and vertically. Vertically, we have a constant acceleration of 9.8 meters per second, and horizontally, we have an acceleration of 0, which is still constant. So in both directions, the acceleration is constant. So if acceleration is constant, this is very useful to us, because constant acceleration, or the existence of constant acceleration, tells us that we can use the Suvat equations to analyse motion, or the equations of constant acceleration, which is what you might call them. Let's look at an example. Now, the first thing that I like to do is to mark all key information onto the diagram. So we have a particle which is projected horizontally with speed 15 meters per second. So there is a speed 15 meters per second from a point 24 meters above horizontal ground. So 24 meters, here we have this measurement here. We need to calculate the time of flight and the horizontal range of the particle. We'll come back to what these mean in just a moment. I'm going to mark on some more information on my diagram. I'm going to label the start of the particle's journey A. I'm going to label this point here the origin. It's almost as if we have a set of axes here. That would be our y-axis and that would be our x-axis. And I'm going to mark this point here where the particle lands on the horizontal ground, point B. Now, I'm going to mark on the acceleration of the particle. Remember, the acceleration is the acceleration due to gravity, and it's downwards, so I'm going to represent it with a double arrow like this, and I'm going to write the acceleration equals g meters per second squared, downwards like that. So let's think about the two directions of motion. We're going to split up and we're going to think about the horizontal direction first of all. Now, there are two ways to think about doing these calculations. One way is to think about the fact that the acceleration is equal to 0, which means speed is constant. And if speed is constant, then we can use the equation speed equals distance divided by time, working horizontally. So where are we looking at in our journey? Well, we're looking at the journey from A through to B, because I want to calculate, part 1, the time of flight. Now, the time of flight, let's make sure we understand what that means, is the time taken to reach the ground. It's a time during which the particle or the projectile is in motion, from when it is launched to when it strikes the ground. And what's this? The horizontal range of the particle. Well, it's this. It's the horizontal distance covered by the particle between the start and the end of its motion. So if I want to calculate these two things, I need to analyse the motion between A and B, and I think it's important to actually state where we're looking at in our journey. So from A to B, we know the speed remains constant horizontally and it's equal to 15. The distance travelled is the horizontal range, which I'll call OB, and the time taken, I don't know what that is, we'll call it T. So let's now have a look at the vertical motion. We'll come back to the horizontal motion again in just a minute. So the vertical motion, remember, the only force acting is the weight, which means the acceleration is constant and equal to 9.8 meters per second squared. So we're going to make use of the Suvat equations. Now, the distance travelled between A and B vertically, we need to choose a positive direction. So I'm going to choose downwards as positive because all of the particle's movement, its motion is acting downwards, acceleration is downwards, the displacement it covers is downwards. So it makes much more sense to choose down as positive here, otherwise you'll have a lot of negative values. So S is equal to 24. Now, U, what is the initial vertical speed of the object? Let's think about that. It is projected horizontally, which means initially, its initial vertical speed is equal to 0. So U equals 0. Now, V is the speed with which it strikes the ground here, like that. We don't know what that is, so we'll call it a question mark for the moment, we'll call it V. The acceleration is equal to 9.8 and the time is equal to the time of flight, which we'll call T. Now I'm going to rule V out straight away because we're not really that interested in it. So S, U, A and T means we can make use of S equals UT plus a half AT squared. So 24 equals a half multiplied by 9.8 multiplied by T, the time of flight, squared. Let's rearrange this and work out what T is equal to. It comes to 2.2131 ... So that comes to 2.21 seconds to 3 significant figures. So we've answered part 1. And we've got the time of flight. Now, how do we then work out the horizontal range? Well, remember, from the horizontal motion, we have this information. 15 equals distance travelled over time. So let's substitute the time into that. And then the distance travelled horizontally, which is the horizontal range, is equal to 15 multiplied by t, which comes to 33.197, etc., which comes to 33.2 metres to 3 significant figures. So we have calculated the time of flight and the horizontal range. Now, Lastly, just going back to the horizontal motion, if you remember, we said that the acceleration is 0 horizontally, which means speed is constant, which means we can use the equation speed equals distance over time. We can also, horizontally, use suvat as an alternative. Now, how would that work? Well, horizontally, S is equal to OB, the horizontal distance covered. U is equal to, in this case, 15, the horizontal speed of projection. V is equal to 15 as well, because remember, the speed remains constant. A equals 0, and then T equals T, the time of flight. Now, from here, depending on what we're looking for, let's have a look at what we could use. So, for instance, if I then apply the Suvat equation S equals ut plus a half at squared, I then find that S, which is OB, is equal to U, which is 15, multiplied by T, like that. And of course, this part of the equation disappears because A is equal to 0. Now, this gives me exactly the same equation that I got over here. So it doesn't matter which method you use horizontally, either use speed equals distance over time or use suvat, just remembering that the acceleration is equal to 0 and the final velocity will be the same as the initial velocity horizontally. Let's look at a second example. So a particle is projected horizontally with a speed of 19.6 metres per second. So let's annotate our diagram. 19.6 metres per second from a point above horizontal ground. Find the distance of the particle from its starting point after 1.5 seconds. So let's call our starting point A. There's the origin. And let's call this point here Q, which is where the time equals 1.5 seconds. So we've been asked to find the distance of the particle from its starting point after 1.5 seconds. So if I draw in this horizontal component here and this vertical component here, the distance that we are trying to calculate is the direct distance AQ, like that. So let's also add on the acceleration, which is G, acting downwards like that. And now we're going to split the motion into the two components, the horizontal and the vertical. Always state which part of the particle's journey you are investigating. We are looking at the journey from A through to Q. So horizontally, we know that speed is equal to distance divided by time. The speed is constant at 19.6 metres per second. Remember, there is no horizontal acceleration. The distance travelled is x and the time taken is 1.5, and we can rearrange this very simply to calculate the value of x, and it comes to 29.4 metres. So now we're going to analyse the vertical motion of the particle, and I'm going to use downwards as positive. As we said, all motion is downwards. And let's write down our suvat information. S is equal to y, u is equal to 0. Remember, the particle is projected horizontally, so there is 0 initial vertical velocity. V is equal to v. We don't know what the velocity is at q vertically. A is equal to 9.8 and t is equal to 1.5. So ruling out v, s, u, a and t, S equals ut plus a half at squared. We can work with that. So y is equal to a half multiplied by 9.8 multiplied by 1.5 squared. So the vertical distance travelled between A and Q, the vertical height covered, comes to 11.025 metres. Now, we can then use Pythagoras' theorem to work out the distance, the direct distance between A and Q, as that would simply be equal to the square root of x squared plus y squared, and we now know the values of those two. So this comes to 31.399 or 31.4 metres to 3 significant figures. Example 3. Let's read the question and then label the diagram clearly. A stone is thrown horizontally, like that, with a speed of 20 metres per second from a point above horizontal ground. By modelling the stone as a particle, find the magnitude and direction of the stone's velocity 2 seconds later. So let's call this point on the journey the starting point A. This is the origin. And let's label a point here which we'll call B. And B is the point at which the time is equal to 2 seconds. Of course, at A, the time t equals 0. So the particle travels downwards. Its acceleration due to gravity is 9.8 metres per second squared. And what we're interested in is the velocity at point B. Now, if we draw on the velocity vector, remember it will be composed of a vertical component, which we need to calculate, and a horizontal component, which is constant at 20 metres per second. So let's analyse the motion from A through to B. And I'm going to start by analysing the motion vertically, because actually, horizontally, I don't need to know the distance travelled, and I know what the horizontal component of the velocity is already. So it actually makes more sense for me to analyse the vertical motion here to begin with. So S equals the distance travelled. We don't know what that is. U equals 0, because remember, its initial vertical velocity is always 0 if it's projected horizontally. V is this, which we're trying to calculate, so that's the key one for us. A is 9.8 and t is equal to 2 seconds. And I should have said very clearly, actually, and make sure you include this as well, that we're choosing down to be a positive direction here. So ruling out S, that then leaves us with these 4 variables to work with. V equals u plus at, and this allows us to calculate the velocity, which comes to 19.6 metres per second, like that. Now, let's calculate the actual magnitude of the velocity. Now we know that the vertical component is 19.6 and the horizontal component is 20. The velocity at B, we'll use vector notation to describe the magnitude here, is going to be the square root of 19.6 squared plus 20 squared, which comes to a value of 28.00 ... metres per second, or 28.0 metres per second, 3 significant figures. Now their direction, we can present this information in lots of ways. I'm going to calculate this angle here, theta, and theta is arctan, or the inverse tan, of 20 over 19.6, which comes to 44.421 degrees, or 44.4 degrees to 1 decimal place. So example 4 is slightly different. We have a particle projected at time t equals 0 with a velocity 5i metres per second. So if you remember, we can take our I vector in the horizontal direction like that, our j vector in the vertical direction like that, and the particle is projected with a horizontal velocity of 5i metres per second from a point with position vector. So this point here has a position vector of 6i plus 50j. So let's call this starting point, point A. Find the position vector of the particle 3 seconds later. So let's imagine 3 seconds later it's at point B where t equals 3 seconds. Now this is actually really similar to one of the examples we've done before, but what we're going to do is approach it in 2 different ways. Let's finish annotating the diagram. I'm going to mark on the acceleration due to gravity downwards like that. So method 1, we're going to split the motion into the 2 components, horizontal and vertical. Let's remind ourselves that we are working from A through to B. That's the part of the trajectory or path that we are investigating. Horizontally, let's have a look at the motion. So we've been using speed equals distance over time, which we can use because the speed is constant as the acceleration is 0. The speed is 5 horizontally. I won't use 5i because we've already said we're working horizontally. Now that equals the horizontal distance travelled, which I'll call x, over the time 3, which gives x equals 15 metres travelled horizontally. I'm going to call this vertical distance y. And let's look at the vertical motion. So we know that we're going to use suvat. Let's identify the information. Choosing down as positive, s equals y, u equals 0. Remember, 0 initial vertical velocity if we are projected horizontally. V is equal to v, we don't know what it is. A equals g, and we do know t, it equals 3 seconds. So I'm going to straight away rule out v, and we keep coming back to using s equals ut plus a half at squared. Let's sub in the information. So y is equal to a half g times 9, and that comes to a value of 44.1 metres. So this measurement here is 44.1 metres. The question, however, asks us to find the position vector of the particle 3 seconds later. So we have to be careful in how we present our answer, because what we're looking for is the position vector relative to the origin. So we're after this vector OB here. So let's remember that whilst the particle has travelled a distance horizontally of 15 metres from here to here, it had an initial horizontal displacement of 6 metres because it started at point A. So the horizontal component of OB, the vector OB, is 21, not 15. It's 15 from point A, but it's 21 from the origin. The same with the vertical motion. Remember, the particle starts off with a vertical displacement of 50j, you can see that here in green, and it's travelled 44.1 metres downwards. This sketch diagram is not drawn to scale. So this vertical measurement over here, which is the height of B above the origin, is going to equal 50 take away 44.1, which comes to 5.9. Again, remember the diagram is not drawn to scale. Now, we could have solved this whole problem differently. Let's have a look at a second method. Now, this second method involves looking at both components of the motion simultaneously and making use of a vector form of one of the suvat equations, and you've come across this idea previously. We're going to use, and we know that it's based on this equation here, r equals ut plus a half at squared plus r0. Now, why is there an additional part to this suvat equation of r0? That's because the motion didn't start at the origin, it started at another point, so we have to include that point in our calculation. So r represents position, or position vector. So r is equal to, now the initial velocity, but as a vector. Well, initially, we start off with a horizontal component of 5 and a vertical component of 0. This is multiplied by the time, which is 3. So just to clarify, we've done this part here. Plus a half. Now the acceleration as a vector, there is 0 acceleration horizontally, but vertically we have a component of negative 9.8, because if we're doing this method, really we're taking I in this direction and j in this direction, which means that because the acceleration acts downwards, we have to include it as negative 9.8 in its vector form, multiplied by the time squared, which is 3 squared. So just to clarify, we've done this part now. We then need to finish off by adding in the initial displacement, so this R0, and the initial displacement is equal to 650 because that's the starting point. So if we simplify this down, perform the calculations horizontally, perform the calculations vertically, you will find you get to the same answer of 21.5.9. So it is possible to do the whole problem as one single vector calculation rather than splitting into horizontal and vertical components. And we will see this concept again. Example 5. A child throws a ball horizontally from a window that is 5 meters above horizontal ground. So if this is my window here at point A, the projectile is launched with a horizontal velocity, and we don't know what that speed of projection is because actually we've got to calculate it in part 1. It just clears a vertical wall. So let's imagine that the vertical wall is here. It's 2.5 meters high and it's 12 meters away from the house, like that. So the particle just clears this. And the ball hits the ground at a point Q, so we'll call this point here Q, and we need to calculate the horizontal distance of Q from the wall. So if we call this W, we are going to have to calculate this distance here. So I'm going to mark on my acceleration, I haven't done that yet, downwards, 9.8 or G. And I'm going to first of all analyse the motion between A and P, which is the top of the wall. So A to P, let's start there. So let's have a look at the motion of the particle horizontally, first of all, from A to P. Now, we know that we can use speed equals distance over time horizontally because the speed is constant. Now, the speed is constant and equal to the initial speed of projection, which we're trying to calculate. Just to avoid confusion with any calculations in the vertical direction, I'm just going to relabel this as capital U horizontally so we don't get that mixed up later on. Now, the horizontal distance travelled is 12. The time taken, we'll call it TP. I don't know the value of that yet. So we have to now look at the vertical motion. We're going to use SUVAT. The distance travelled vertically. Now we'll choose down as positive, which allows this distance travelled vertically to be positive. It's 2.5 because P is 2.5 metres above the ground and we start 5 metres above the ground. U is equal to 0 vertically initially. V we don't know. A is equal to 9.8. And T is equal to TP. We don't know the value of it. Let's rid ourselves of V, as we don't need it and aren't asked to calculate it. S equals UT plus a half AT squared. 2.5 is equal to a half times 9.8 multiplied by TP squared, and you can work out the time taken to reach point P. It comes to 0.714 ... seconds, and I'll store that in a calculator memory. Let's call it memory T. And we can then go back to the horizontal calculation and we can work out the speed. So U is equal to 12 divided by TP, which comes to 16.8 meters per second. Now let's have a look at part 2. The ball hits the ground at a point Q and we need to calculate the horizontal distance of Q from the wall. So we can analyse the motion between P and Q, or we can look at the motion from A all the way to Q. There are lots of different ways of solving these problems. Please do experiment with different methods, see if you get to the same answers successfully. I'm going to look at the motion from A to Q. Now, horizontally, I know that speed equals distance over time, so U is equal to the distance horizontally, which is 12 plus, let's call it WQ, over the time taken, which we don't know either. We'll call that TQ. But we do know the value of U, it's 16.8, so 16.8 equals 12 plus WQ over time taken to reach Q. And vertically, we can calculate this time taken to hit Q and then go from there. So A to Q downwards is positive, S is equal to 5 meters, U is equal to 0, V we don't know, A is equal to 9.8, and T is equal to TQ. So it's very similar to the previous calculation. Rule out V. We'll use S equals UT plus a half AT squared and fill in our values. And this gives us the time taken to reach point Q, which comes to 1.0101 ... seconds. And we can substitute that time into this result here, which then gives us our value for WQ. So I will let you follow through the calculations yourself, rearrange carefully. You will find out that WQ comes to a value of 4.970 ... or 4.97 metres to 3 significant figures. Let's have a look at our last example. A tennis ball is served horizontally at a speed of 24 metres per second from a height of 2.7 metres above ground. So we're going to assume that the tennis ball is released from this point here, A. The net is 1 metre high and 12 metres horizontally from the server. So let's put the net here, 12 metres away from the server and 1 metre high. We'll call this point P and we'll call this point N for net. Determine whether the ball clears the net and if so, by what distance. So mark on the acceleration of the particle, vertically, acceleration due to gravity. We are going to investigate where the particle is vertically when it is a horizontal distance 12 metres away from its starting point. If its height is more than 1 metre above the ground, that's fantastic, it will clear the net. If not, it won't clear the net, it will hit the net. So find out what happens to the particle vertically when horizontally it is 12 metres away. So essentially we're sort of analysing the motion between A and N. Let's have a look at the horizontal motion, and speed equals distance over time. Let's keep reminding ourselves of that. Speed is equal to 24, distance is equal to 12, and time is equal to time. And this rearranges very easily to give us t equals 0.5 seconds. So when the particle is 12 metres horizontally from its starting point, that takes a time of 0.5 seconds to get there. So what we now want to know is what is happening vertically at this time. So S equals question mark, let's find it out. U equals 0, V we don't know, A equals 9.8 and T equals 0.5, and of course everything downwards is positive in this example. So ruling out V, S equals UT plus a half AT squared. We can work out the vertical distance travelled after 0.5 seconds, which comes to a value of 1.225 metres. So that means if we travel 12 metres horizontally from the starting point like that, we have travelled a distance of 1.225 metres vertically downwards. Now, are we above the net or below the net? Well, let's find out by working out 2.7 take away 1.225 metres, and that will tell us our vertical distance above the ground, which is 1.475 metres. So that means we are above the net because the net is 1 metre high. So 1.475 metres is greater than 1 metre, so the ball clears the net by 0.475 metres. So the diagram isn't quite like this. What we have is a measurement of 1.225 metres and there's the net 1 metre high. None of this is to scale. So we clear by 0.475 metres. So it looks a little bit more like that.